Hello and welcome to this video where today we're going to have a look at projectiles and projecting them at an angle. So in the last video we had a look to actually see how it was that we attacked or approached projectile questions, and what we saw is that we could use our Suvat equations for projectiles, and that can be done because acceleration is a constant. Because as a really quick reminder, as something flies through the air, the only force that's acting on it is its weight downwards, and its weight is equal to mg, where m is the mass of the object and g is the gravitational field strength, which we can also take to be the acceleration due to gravity, which for us on the Earth is 9.81 meters per second squared. And the key idea, the most important idea that we had, was that the motion in the vertical plane is independent to the motion in the horizontal plane. In other words, we can treat the horizontal motion and the vertical motion completely separately, because basically it's like an object is accelerating downwards, but because it's moving at a constant speed across like this, basically what will happen is it will make this type of shape, so it makes like a parabola. So we had a look what happened when we projected something horizontally. So it started off horizontally and it fell and made this type of shape. What we're going to have a look at today is what happens when, instead of projecting it horizontally, we just project it at an angle, so it goes up and then comes back down again. So we can do exactly the same thing. There's just one extra step that we need to do, and what we need to do there is we simply need to resolve our velocities. So if we're told, for example, that the initial speed of an object is v meters per second, so it's so many meters per second, and it's projected at an angle of whatever degrees to the horizontal, then all we have to do to use our method where we look at things horizontally and vertically is to work out what the initial velocities are horizontally and vertically. So we just resolve. So in this direction, the horizontal velocity to start off with would just be v cos theta meters per second, and then you'd have also a vertical velocity upwards of v sine theta meters per second. And then once you've done that, what you've basically done is you've split up your initial velocity into a horizontal and a vertical component, and from that you can basically work out whatever it is that you need to work out. So that's really the only kind of theory, if you like, that we really need. So we'll have a look at an example. So what we're going to look at is we're going to look at this. So what we've got is we have a cannonball. It fires a cannonball at a speed of 200 meters per second, which potentially might be a little bit faster for a cannonball, at an angle of 30 degrees to the horizontal. So basically what's happening is that this thing is being projected like that, where that should be a straight line, and this angle here is 30 degrees. And what it will do is it will continue to move upwards, and then it will move back downwards, only under gravity, so the only force acting on it is gravity, and it will make our characteristic parabolic shape. So what we need to do is three things. We want to find the maximum height of the cannonball, so that's basically how high it was at its centre. We want to find the time of flight, so how long it was in the air for, and then we want to calculate the range of the cannonball. Well, the range, if you remember, is the horizontal distance from where it takes off to in this case where it lands. So I'm just going to do exactly the same thing that I did last time. I'm going to start off thinking about what's going on horizontally and just write our Suvat quantities down. So if we think about it, our displacement horizontally, well, that's the range that at some point we want to work out. We don't know that. Our initial velocity, well, our initial velocity is 200, and we're going this way, so we're resolving horizontally, is equal to 200 cos 30, like that. So we can work that out on our calculator later on if we need to. And our velocity horizontally is again exactly the same thing, because there's no acceleration in that direction, so it carries on doing exactly the same thing as before. Acceleration is 0 meters per second squared, and time again is something that I don't know. So potentially both of these things are something that I'm going to need at some point. Okay, so if we think about going up vertically, so I'm going to start off with A, because it may well be that we have different things going on vertically for A, B and C. So we'll think about just A. I want to find the maximum height of the cannonball. Well, if I think vertically, what the maximum height happens when this thing moves upwards, and then just as it gets to the top of the flight, it's going to start to come downwards. So here, at this point up here, at least vertically, not horizontally, but vertically, its velocity is going to be 0. So it's the maximum height, the displacement, is the thing that I want. So I don't know what that is. Its initial velocity when it first sets off is equal to 200 sine 30 meters per second. Its final velocity when it gets to the top is going to be equal to 0, because just as it gets to the top, it slows down, it becomes 0, and then it starts moving again. So that's 0 meters per second. Acceleration, the same as always, is minus 9.81 meters per second squared, and the time again is something I don't know, so I don't know that. So what I would like to do is, to find the maximum height, I need to use some of these quantities in order to do that. But I only have to think about this in this case, because height's got nothing to do with horizontal motion. So I only have to think about these things. So the equation I can use for part A, so for part A, if I want to know, I know the final velocity, I know the initial velocity, I know the acceleration, I want the distance. So I could use v squared is equal to u squared plus 2as, because I know everything apart from the displacement upwards. So I can put my numbers in. V squared, well, the final velocity is 0, so that squared is equal to 0. The initial velocity squared, well, 200 sine theta, if I do that on my calculator, it actually works out to be 100 meters per second. So I've got 100 squared plus 2 lots of the acceleration, which is minus 9.81, and it's minus again, if you remember, because it's going downwards and we're thinking about motion upwards, multiplied by the displacement, which is the thing that I want. So if I do that, if I rearrange this, I get the displacement is equal to essentially 100 squared over 2 lots of 9.81. And if I do that on my calculator, I get approximately 510 meters. So this thing travels 510 meters up in the air before it starts to come back down again. So that was part A. For part B, I want to find the time of flight of the Cannonball. So this time, this will potentially, at least from a vertical point of view, be something different. So what I'm going to do is I'll now take this and I'll get rid of it. And we'll have a think about what's happening from a time of flight point of view. So from a time of flight point of view, basically what's happening is this thing's starting here and it's going over here and it's landing back down here. So in terms of displacement, I don't know displacement from when it starts off to when it lands down here. In actual fact, that's what I'm asked for in part C, so I don't know that. Its initial velocity is something, again, that I know, and as we worked out before, that was 100 meters per second. Its final velocity downwards, so that was 100 meters per second upwards. Its final velocity from a vertical point of view would be minus 100 meters per second from a symmetry point of view, because it gets projected upwards with a velocity of 100 meters per second. So when it comes back downwards, it'll hit the floor with a velocity of minus 100 meters per second. Its acceleration, as always, again, is minus 9.81 meters per second squared, and the time is the thing that I want to know. Now, there's two ways to approach this problem. What you could do is you could do a very similar thing to what we did in the last question. We could actually work out how long it took to go from here up to the top, just like we did before. So in part A, we worked out the height up to the top, so we could use that, and what we could do is work out how long it took to get to the top, and then to get from the top back down to the bottom again is the same amount of time. So for example, if it took 2 seconds to get from here to the top, it would take then 2 seconds to fall from the top back down to the bottom, so the total time of flight would be 2 add 2, so therefore would be 4. However, there are sometimes questions where you get things where you want to know, for example, a wall is put in the way and you want to know how long it would take to just clear the wall, or if it's dropping down further than the ground, so if the ground slopes or something like that. And so you can't use this symmetry argument, so you just have to use some maths. So we're going to do the mathematical way. So what I want to do with this, again, this is a little bit like a question we had in a previous video, because if you think about it, there are 2 times when this ball is on the ground. Basically, when it started and when it finished. So what I'm going to do is I'm going to use this equation here, because I know basically everything I need to know in this equation, apart from the time, which is what I'm looking for. Because when this thing has gone through its total time of flight, the vertical displacement is 0, so I know that this is 0. So I know that's 0. Initial velocity is 100 meters per second. Acceleration is minus 9.81 meters per second squared. T is what I need to know. So if I put my numbers in, 0 is equal to the initial velocity, which is 100, multiplied by t, which is what I would like to work out, plus half of the acceleration minus 9.81 meters per second squared, multiplied by t squared. And again, I've got a quadratic, but it's a slightly easier quadratic than actually being able to use the formula, because this is 0 and I've got 2 t's here, so I can take out a common factor of t. So if I do that, and if I take out a common factor of t and rearrange it very slightly, I get t into 9.81 t minus 200 equals 0. So basically what I've done is I've taken out a common factor of t and also multiplied both sides by 2 at the same time. So if I do that, then I can see that obviously t equals 0 is one of our solutions to this equation, because if I make t 0, the whole of this side is multiplied by 0, so that solves that, and obviously that's the starting point, and that makes sense because the displacement upwards would be 0 when the time is 0. The bit inside the brackets is the bit we're interested about, because that'll tell us the time when it gets to the end point. So if we look inside the bracket, what we actually find is that what we'd have, in order for this to be true, 9.81 t minus 200 would also have to equal 0, because then I'd have t multiplied by this bit in brackets, which is equal to 0. And so now I've got a really nice simple equation that I can solve. So basically I end up with t equals, so I add 200 to both sides and divide by 9.81 like that, and if I do that, and do that on my calculator, I end up with basically 20.4 seconds. So this thing is in the air for 20.4 seconds. We shoot it, it gets shot out of our cannon. 20.4 seconds later, it lands on the ground a certain distance away over here. So what we can say is that the vertical motion is in the air for 20.4 seconds, so I can fill this in here, 20.4 seconds. But also, if you think about it, from a horizontal point of view, the time's the same. It can't be in the air for a different amount of time horizontally than it can vertically. So those 2 times are the same. So now what I've done is I've worked out this time, I can put it into here, and then I can answer part C. So if I look at part C, and again we get rid of this, just so we can keep all of our information over on the left hand side. If we look at part C, I want to work out the range of the cannonball. So the range is, if we remember, is the horizontal distance from the starting point to where it lands. So if I'm looking at this thing, I can either use Masuva equations, or I can know that because the acceleration is 0, I can simply use speed is distance over time. So that's what I'll use. So I know that basically, well, velocity, the better way of saying it, velocity is equal to the displacement divided by the time. And so if I just put my numbers in, then the displacement is what I'm looking for. The velocity doesn't change because the velocity is always 200 cos 30, and the time is the time that we've just worked out. So if I rearrange this equation, I get that the displacement, which is what I'm wanting to calculate, is equal to 200 cos 30, and that's just something I can do on my calculator. And I multiply it by the time, because I've rearranged this equation, which is 20.4 seconds. And if I do that on my calculator, I end up with 3 significant figures, 3,530 meters. So that is the horizontal distance that this thing travels, in other words, the range of the cannonball. So that's a very typical projectiles type of question. You're asked to work out something using, for example, the vertical components of the velocity, and then you take that answer and then use it to then calculate horizontal distance or horizontal velocity or something along those lines. But you take one value, put it into the opposing value, if you like. Projectile questions come in lots and lots of different types. So, for example, you could be asked to work out the time from this one and then use that to work out something on this side. It's simply what the question asks, and there are lots of different ways that the question can ask it. To be fair, most of the time you start off with vertical components and then you take it and you look at the horizontal components, but not every single time. So that was projectiles at an angle. Thank you very much for watching, and I'll see you again soon.